In most cases, clinically, the first task is to choose the best topography that was gained when the patient was in the office. In this case, you can see there are 4 topographies of the right eye, and our mission first is to decide which one of these maps do we want to use to design a contact lens. So what I'll do is I will place the cursor on one of the maps and right click, and from the drop down menu I'll choose E-value plot. And I can see for these 4 topographies their values varied somewhat. It looks to me from this distribution that either map number 1 or map number 3 would be our best bet. So we would eliminate 2 and 4 and say it's either 1 or 3 based on the distribution of eccentricities from these different maps. Another way to approach it is to use the repeatability check, and if we use that criteria we can see that repeatability wise that number 3 is actually preferable to number 1. So using this criteria combined with the other, we eliminate now map number 1, and it will be map number 3 that we'll use to design our contact lens. So I'll go to map number 3 and I'll remove the other maps from the screen so that I have more workspace, and from this I'll go to photo process. Photo process is very important because this is how you really decide where the quality portions of the map are and where the distorted portions of the map are. I'll enlarge this to full screen mode. The computer is looking at this black and white photograph of this Placido's disc reflection from the cornea, and the human eye, as you sit and look at it, you can see it yourself. All of the data that we use when designing contact lenses with WAVE is obtained from the topographer, and the topographer gets all of its information from this black and white photograph that's captured with the equipment. When we look at this with our naked eye, we can see several things ourselves, just using our own brains to analyze this reflection. This is a reflection of Placido's ring disc off of the cornea, and we can see that these are some eyelashes up at the top, and we can see this little white streak up here, and we know that that's a tear meniscus up there. That's not a reflection of anything, that's the tear meniscus. And we can see that down below also. So we can see a meniscus of tears along the border of this eyelid. We also see this little bright spot over to the side. That's probably the equipment, that little light on the equipment that reflects off of that. We can see several things. The computer software does an analysis and looks for rings and rings only. And if I turn the rings on, you'll see this is the way that the computer saw this image. It actually thought that there was some reflection up here, and it created a distortion in the inferior and superior part of this map. It also gets a little wavy out here. So also the computer was looking for the pupil, and if we turn the pupil on, we can see that it roughly estimated that the pupil was about this big. But we can clean up some of the distortion in this map. I'm going to use the eraser function within the Scout software, and what this enables me to do is to take the cursor with the mouse and place it over areas that appear distorted to my own eye, and by holding the left mouse button it changes the color of these from either red or green to a purple color and eliminates them from the data that we use to design and analyze the cornea. So I'll hold the left mouse button down here and I'll drag over these distorted areas in this upper area, and down below also along this lower lid. I want to get the entire area where the tear meniscus was distorting the rings, and I'll click OK. Now the software will show me the effect of my editing, and you can see that I removed a lot of the distorted areas superiorly and inferiorly simply by using this eraser function to eliminate the distorted regions of the cornea. This is a very quick and easy way to clean up your source topography. It's always best to get a good topography in the first place, but in reality, in a clinical setting, quite often you'll find that you need to do some editing. I will now go ahead and extrapolate this data and save it so that I can use it for contact lens design. I'll click the extrapolate button, click here, here, and about there, and then save the test. Now that we've edited and extrapolated the data, the whole point of this was so that we could have some information that we could make clinical decisions for this patient. I like to look at the source map originally. That's where the most pristine information is available. And the very first thing I believe you should look at is for symmetry. In this particular instance, if we look at this cornea, we can see that we have flatness nasally more so than we do temporally. However, if we look at the way this data is distributed on this particular cornea, you can see that the data is somewhat discentered over in the nasal direction, considering this is the right eye. So we're actually about a half millimeter from the limbus where this flat information is, and on this side we're a millimeter and 3/4 away. So if this data did continue out, it probably would get just as flat as this. So that's probably not altogether that much of an asymmetry necessarily. On the other hand, if we look at the superior half of the cornea compared to the inferior half of the cornea, we can see there is a difference. The superior portion seems to be smoother and more regular. The inferior portion seems to have a flat area and a steep area. This particular patient, if you were to stand in front of her and look at her, you would see that she has very tight lower lids and a fairly deep set eye. This is not a real large cornea. If you look at the overall scale, it's about 11 or a little bit less millimeter cornea. So this is a fairly small eye, a fairly steep eye, and some pretty tight lids. And this inferior section here that looks asymmetrical with the superior half, this is most likely just a little ridge from a tight lid, but we better keep that in mind that she does have tight lids. In this case, I would be thinking I'm using a gas permeable lens to fit this patient, and one thing that I would conclude just looking at the quality of the data here is that this lens will most likely not ride high. If anything, it will probably center or ride a little bit low, and she's got pretty tight lids and a pretty small eye, so I better keep my lens small and thin, and it's going to center or ride a little bit low. Just looking at the steepness and the asymmetry and the qualities that come from this map, that's my intuition, is that that's how a gas perm lens will fit on this particular cornea. It doesn't take very long before you can see a wide variety of presentations when you properly analyze your topography information. This cornea, for instance, has a significant inferior steep area, and I could anticipate that the lens would ride quite low on this eye. In this case, we see distortion and we see asymmetry, but with experience you will learn that what this is a imprint from a contact lens. This arcuate quality to this inferior steep area is quite unnatural appearing and too smooth and regular. This patient has been wearing a gas permeable lens that was apparently riding high. Now that's a good tip-off. You may have the same experience when you design a lens for this same cornea. The upper lid may be tight or something and causing the lens to ride high. I would say in all likelihood this cornea has a significant amount of toricity to it. That may have been in fact why they were originally put into a contact lens. But they may be wearing a spherical lens, and a spherical lens on a toric cornea does have a tendency to decenter, particularly when there's a very significant amount of cylinder on that cornea. In this case we have approaching 2 diopters, so most likely this patient was wearing a gas perm lens that was spherical and riding up high. And depending on what their current results are like, I may not worry about this inferior steepness at all. It depends on the clinical setting, but you will learn from experience how to differentiate distortion induced on the front of the front of the cornea by a gas perm contact lens from a true anatomical asymmetry on the cornea. And then of course you have the other type of maps that are difficult to obtain and have a lot of distortion in them, but still once you clean up the data you can see a pathological asymmetry. This is genuine. This is a cone, a keratoconus patient, where the apex of the cone is decentered down and to the right significantly. So you would anticipate your contact lens will have a strong tendency to pull to be pulled down and to the right in this type of situation. Anticipating that lens decentration is very helpful when you're designing your contact lenses. In post-refractive surgery cases, peripheral asymmetry becomes just as important as anything else. As you can see on this post-surgical cornea now, the inferior section is quite a bit steeper than the superior, and so you could anticipate that a lens would have a tendency to be pulled down. Now, there will be a reverse geometry type of lens on this eye, but nevertheless there still will be a tendency for the lens to be pulled down to the lower half of the cornea rather than riding up high.